In this video, we are going to do a recap of all the techniques we learned for handling square roots. So that means we're going to take a look at calculating square roots, at simplifying expressions involving square roots. We're going to take a look at factorizing. So why and how can we turn a square root like square root 50 into a square root with a smaller number underneath the square root sign. And at the very end, we're also going to look at how we simplify expressions involving brackets and especially remarkable products, such as this one. But we're going to start with the basics. We're going to start with calculating square roots. So that means we're going to learn how to add, subtract, multiply, and divide square roots. And we're going to look into how we handle the square roots of fractions, square roots of large numbers, and of decimal numbers. As you know, taking the square root of a number basically means that when you know the area of a square, you try to find out the side. So for example, if we take the number 81, if we look at 81 as the area of a square, then what is the side of that square going to be? Well, the side of that square has to be a number whose square is going to be 81. So if I take the multiple, if I multiply that number by itself, I get 81. So of course that number in this case is going to be 9. So that means the square root of 81 equals 9. So usually when you have very simple numbers, what you're looking for is this. You're going to look for a number that if you multiply it by itself, you get back your original number. So let's look at this principle in slightly more complicated situations. So just addition of square roots. Okay, so what do we have here? We have the square root of 16 plus the square root of 9. Well, both of these we can solve independently, right? So the square root of 16 is 4, the square root of 9 is 3. We can add those two numbers, 4 plus 3 equals 7. We can also see an example here where we have something to solve underneath the square root sign first. So here we take the square root of 16 plus 9. So we will have to calculate 16 plus 9 first. That's 25. So we are taking the square root of 25. And the square root of 25 is 5, because 5 squared is 25 again. As you see, these two are different. Taking the square roots first and then adding is different from first adding and then taking the square roots. And a slightly more complicated example, we take the square root of 20 minus 4, and then we subtract the square root of 1 plus 8. So we solve both of these underneath, we calculate both of these underneath the square root signs first. 20 minus 4 is 16, and 1 plus 8 is 9. So we are taking the square root of 16, which is 4, and then we subtract the square root of 9, which is 3. So 4 minus 3 equals 1. If you want, you can pause the video here and see if you can calculate these by yourself, and then afterwards see if you got these right. So let's take a look at the answers. Here we need to subtract these two numbers first, and we get 144. So the square root of 144 is 12, because 12 squared is 144 again. Here we take the square root of 169 first, which is 13, and we subtract 5, so we get 13 minus 5 is 8. And here we add these numbers first. That gets us to 100, so the square root of 100 minus the square root of 36, which is 6, minus the square root of 64, which is 8. Square root of 100 is 10, so we get 10 minus 6 minus 8. That's 10 minus 6 is minus 4, and is 4, sorry, and 4 minus 8 is minus 4. Now let's take a look at multiplication. And we're going to see that that works in a very different way. Let's look at these first. Square root of 16 times the square root of 9. Well, we can solve these separately, right? So we can take the square root of 16, that's 4, multiply by the square root of 9, that's 3, so we get 4 times 3 is 12. Now, what if we take a similar example, but we multiply these two numbers first, and then we take the square root? So what do we get? 16 times 9, that's, well, 16 times 10 is 160, minus 16 is 144. So we are taking the square root of 144. What is that? Well, that is 12 again. And this is not a coincidence. It turns out it doesn't matter if you take the square roots first of two numbers and then multiply them, or multiply them first and then take the square roots. And take the square root. And that's quite interesting. If you want to understand why that is the case, you can get a sort of feel for that by squaring both of these expressions. But you can also just take it as a given, that it doesn't matter if you take the square roots first, then multiply, or multiply first and then take the square root. And that helps us often when we have to figure out the square roots of numbers that we can't actually take the square root of, right? We can't take the square root of 2. We cannot take the square root of 8 either, but what we can do is, instead of taking the square roots first and then multiplying, we can multiply these numbers first and then take the square root. So the square root of 2 times the square root of 8 is the same as multiplying 2 by 8 first and then taking the square root. And it turns out we can do that because 2 times 8 is 16 and the square root of 16 is just 4. So this is a very handy way of calculating square roots that you otherwise couldn't calculate. Let's look at a few practice examples. So, square root of 4 times 9. 4 times 9 is 36, so this is the square root of 36, which is 6. Here, this says 2 times the square root of 9, so we get 2 times 3, of course, and 2 times 3 is 6. Square root of 3, we don't know how to calculate that. Square root of 27, impossible, but what we can do is say, rather than taking the square roots first and then multiplying, we can multiply these two numbers first. 3 times 27 is 81, and then we take the square root of 81, which is 9. So we can calculate this expression as a whole. Now, division is basically just the inverse of multiplication, so it works basically in the same way as multiplication. So what do we get here? If we take the square root of 64 divided by the square root of 16, well, we can calculate these separately. Square root of 64 is 8, square root of 16 is 4, so this turns out to be 8 divided by 4. 8 divided by 4 is 2. Now, what if we, instead of taking the square roots first and then divide these numbers first and then take the square root of the result? What do we get? 64 divided by 16, that's 4. So we are actually taking the square root of 4, and that's 2. So just like with multiplication, these two are the same and we can switch between them whenever it suits us. And it suits us, for example, in this case, where we have the square root of 8 and the square root of 2, and we're dividing these two by each other. We can't do those separately. And what we can do is say, okay, so let's divide them first and then take the square root. So we can divide 8 by 2, gives us 4. So actually what we're doing is we're taking the square root of 4, and that's easy. That's just 2. So a few practice examples again. So let's look at these. Here we're taking the square root of 450 divided by 2. What is 450 divided by 2? That's 225. So we're taking the square root of 225, and that is 15. Here we are taking 2 times the square root of 100 and dividing by the square root of 25. Square root of 100 is 10, so 2 times 10 divided by 5. So 2 times 10 divided by 5 is 20 divided by 5 is 4. In this final case, we can't calculate these two square roots separately. Square root 27, can't do that. Square root 3, can't do that. What we can do is we can divide the two numbers first and then take the square root of the result. So we can divide 27 by 3. That's going to be 9. So we are actually taking the square root of 9, and that is 3. So the technique we just saw also helps us when we take the square roots of weird numbers, for example, of very large numbers or very small decimal numbers or fractions. And in order to apply that, we are going to need to know what the square roots are of what we call powers of 10. So you know that when I take 10 squared, that is actually 10 times 10, so that's 100. When I take 100 squared, that's 100 times 100, so that's 10,000, and 1,000 squared is 1 million. So I know that the square root of 100 is 10, the square root of 10,000 is 100, and the square root of 1 million is 1,000, and so on. And that means that if I take the square root of a large number that I maybe don't see immediately, what I can do is I can split that number into two factors. So I can say instead, rather than the square root of 1600, I recognize that there is a 16 here, and the 16 has been multiplied by 100. And now I know it doesn't matter whether I multiply these two numbers first and then take the square root, or take the square roots of them separately and then multiply the result. So I can just take the square root of 16 and the square root of 100 and then multiply those two numbers. So the square root of 16 is 4, square root of 100 is 10, and I can multiply them afterwards, and that gives me 4 times 10 is 40. Another example, this is a very big number. I don't immediately see what the square root is going to be, but I recognize the number 225 here, and I see it has been multiplied by 10,000 because we've added 4 zeros. So this is actually 225 times 10,000, and I can take the square roots of these two numbers separately and then multiply them. So I know the square root of 225 is 15, square root of 10,000 is 100, and then I can multiply these two numbers, and it turns out that the square root of 2,250,000 is just a very friendly 1,500. Okay, so the square root of 900, well, maybe you see that immediately, but if you don't, then you can say this is 9 and it has been multiplied by 100. And I can take the square root of 9, that's 3. Square root of 100 is 10, so this is 3 times 10 is 30. This one is a bit more difficult, 1,690,000. So I recognize that there is a 169 here, which is 13 squared, and it has been multiplied by 10,000. So I can rewrite this as the square root of 169 times 10,000. And instead of solving this at once, I can look at them separately. Square root of 169 is 13, and the square root of 10,000 is 100. So this is 13 times 100 is 1300. And the square root of 250 times the square root of 40, well, so what we can do is we can say, let's multiply these two numbers first and then take the square root. So this is 250 times 40. Well, what is that? 250 times 4 is 1,000, times 10 is 10,000. So we're taking the square root of 10,000. And the square root of 10,000 is just, we already see it here, that's just 100. We can apply the same trick when we look at small numbers or decimal numbers. So I recognize that there's the number 25 here. And what has happened, what have we done to this number in order to get 0.25? Well, we moved the decimal point from here to here. So we moved it 2 places. So apparently we divided by 100. So 0.25 is the same as 25 divided by 100. So even if I can't calculate this at once, I can rewrite it as the square root of 25 over 100. And now instead of taking the square root of this whole number at once, because this is a division, I can take the square roots of these two numbers separately and then divide them. So I can take the square root of 25 first, that's 5. And I can then take the square root of 100, that's 10. And then After that, I can divide these two numbers, and then 5 divided by 10 gives me 0.5, or 1/2, whatever you prefer. Similar example, 1.69, the square root of 1.69. I recognize that there is the number 169 somewhere here, which is 13 squared. But something happened to it. What happened? Well, we moved the decimal point by 2 places, so we divided by 100. So we can rewrite this as 169 over 100. And again, we can calculate these two numbers, the square roots of these two numbers separately, and then divide them. So then this becomes the square root of 169 is 13, and this becomes the square root of 100, and that's 10. And then I divide them. 13 over 10 is 1.3. So the square root of 0.04. So be careful here. That's not just going to be 0.02. If we are careful, then we see that this has the number 4 in it. But what happened to it? We divided this number 4 by 100. So this, we can rewrite this as the square root of 4 over 100. And now we can take these two square roots separately. So we can change this. We can rewrite this as the square root of 4 over the square root of 100, because these two expressions are always equivalent. And then I can take these square roots, of course. Square root of 4 is 2, square root of 100 is 10, and 2 divided by 10 is 0.2, or 1 over 5, whichever you prefer. Similarly, square root of 2.25, we recognize the number 225 here, but it has been divided by 100 again. So I can rewrite this as square root of 225 divided by 100. And the square root of 225 is 15. Square root of 100 is 10. So this is 15 over 10. So this is 1.5. As a final example, the square root of 2 and a quarter, so 2 and 1 over 4. There's two ways you can do this. You can say, okay, so this is actually the same as the square root of 2.25. So I can just do this again. Or what you can say is I can turn this into an improper fraction. So I can look at this 2 and see that 2 is actually the same as 8 over 4. So I have 8 over 4 and 1 over 4. So this is actually the square root of 9 over 4. And then I can look at these numbers separately. So this is the square root of 9 over the square root of 4. Square root of 9 is 3. Square root of 4 is 2. So this is 3 over 2, which is 1.5. So these two give me the same result, of course, because it's the square root of the same number.